So in this video lesson, we're going to have a look at limiting reagents. And then we're going to talk about percent yield. Now, before we can talk about limiting reagents, you have to make sure that you have a good handle on using the mole ratio and using stoichiometry. So if you don't have a good handle on that and you need to do some more practice, please go back and practice mole ratio and stoichiometry before looking at these limiting reagents. So when we are dealing with a reaction, a limiting reagent is going to be, so we're going to just define limiting reagent here. It's going to be the one that dictates, so the compound, whatever it happens to be, that dictates how much can be made. The idea is that it's going to limit how much product can be produced. Now, we also can have an excess agent. So that excess reagent is the compound or substance that you have more of than you need. So the excess reagent you'll have left over. Okay, now the easiest way to think about a limiting reagent and an excess reagent is actually if we think about making chocolate chips. So if we think about baking, sorry, not making chocolate chips, making chocolate chip cookies. There we go. So if we want to try and make chocolate chip cookies, two of the big things we need is we need flour and we need chocolate chips. Right? Of course, we need some other things in our recipe for chocolate chip cookies, but the two big main ingredients in chocolate chip cookies are chocolate chips and flour. Right? All right. So in a regular recipe for chocolate chip cookies, you might need, 4 cups of flour and maybe 1 cup of chocolate chips, or maybe 2 cups. It depends on the recipe you're using. We'll go with 4 cups and 1 cup. So if we're trying to make this recipe for chocolate chip cookies, we need 4 cups of flour and we need 1 cup of chocolate chips in order to make this batch. Okay. Now, if we only had 2 cups of chocolate chips in total, then we could only make 2 batches of this recipe, even if we had an unlimited amount of flour. So even if I have a whole bag of flour, so in this scenario, we have an entire bag of flour, but we only have 2 cups of chocolate chips, which means we can only get 2 batches made of this chocolate chip cookie recipe, right? Because as soon as we make 1 batch, we're going to use 1 cup of chocolate chips. And then as soon as we make the second batch, we're going to use up our second cup of chocolate chips. And then we're out of chocolate chips and we can't make any more cookies. Okay, no matter how much flour we have. Now, in a different scenario, maybe I have, I've got like 28 cups of chocolate chips. I bought the entire store worth of chocolate chips, but I only have 12 cups of flour. Because that's all I could find at the grocery store right now. So in this scenario, we could make 3 batches because each batch is going to use 4 cups of flour. So we could do that 3 times. And we'd have more than enough chocolate chips to do that. But then once we used those 3 batches, we'd be running out of flour. So in our first scenario where we had an entire bag of flour and 2 cups of chocolate chips, the chocolate chips were our limiting reagent and our flour was in excess. in the second scenario where we have only 12 cups of flour but 28 cups of chocolate chips, our chocolate chips are in extreme excess and our flour is the limiting reagent. So depending on the situation, we can have a different substance being our different limiting reagent even within the same reaction. Now the idea is that the limiting reagent is the thing that is going to limit how much you can make. Okay, so as soon as you run out of it, you can no longer do the reaction and you're not able to make any more product. Okay, so we are going to have a look at an actual reaction, and we are going to talk about using limiting reagent and doing limiting reagent questions with actual chemical reactions. So the reaction we're going to look at is going to be H2 plus O2, and it's creating water. We've seen this reaction before, and we need to balance it out. So we need a 2 here in front of our H2. You know what? Let's put that in red. So we're going to balance it. So we're going to put a 2 here in front of our H2, and then we're going to need a 2 in front of our H2O so that we can balance out our hydrogens, balance out our oxygens. Okay? So in this reaction, we're going to say that we have got 45 grams of hydrogen. So we have 45 grams of hydrogen, and we have 100 grams of oxygen. Okay, and I want to know how much water that's going to make. Plus, I want to know which one of those product or reactants is our limiting reagent. So which one is limiting and which one is excess. Now the nice thing is that we only have two reactants, and so whichever one is the limiting reagent, obviously the other one has to be in excess. So we are starting with 45 grams and 100 grams, and we want to know which one of those hydrogen or oxygen is going to limit how much water we can make. So the best way to do this is to actually use stoichiometry to figure out how much water we can make if hydrogen was a limiting reagent, and then do the same thing but pretend it was oxygen, and then see which one makes less. Okay, so we're going to start out with, we're going to assume, so if hydrogen was the limiting reagent, and again, we don't know that hydrogen is, we're just starting out with hydrogen. We're saying if it was a limiting reagent, how much water could we make? So we start out with our 45 grams of hydrogen, and then we want to turn that into moles. So we're going to use our mole ratio, that 1 mole of hydrogen is going to be 2.02 grams, okay, for hydrogen, and we're going to keep the hydrogens in there. And so that's going to allow us to cancel out our grams of hydrogen. And this should look familiar because now we're using this mole ratio in stoichiometry. So then we want to go from moles of hydrogen to moles of water. And so to do that, we're going to use another conversion factor. And so we're going to put our moles of hydrogen on the bottom. We need our moles of water on the top. And the mole ratio, 2 moles of water for 2 moles of hydrogen. And that's going to allow us to cancel out our moles of hydrogen. And if we ended there, we'd be left with the moles of water. But I think we should go to the mass, okay, just in terms of how much water we're going to make. So we're going to add one more conversion factor here. And we know that 1 mole of water is going to be my 18.02 grams of water. That's our molar mass for water. Okay, and so then when we do that math, we are going to work out to 401.5 grams of water. Okay, so if hydrogen was the limiting reagent, we'd make this 401.5 grams of water. Now, we're going to do exactly the same thing, only this time we're going to say, what if it was oxygen? So if oxygen was our limiting reagent, how much water could we make? Okay, so we're going to start out with our 100 grams of oxygen, and we're going to turn that into moles. We're going to do the exact same type of calculation. And again, I want to remind you, this calculation is exactly the type of calculation that we did in stoichiometry. So we are not learning a new calculation. We're just using this calculation in a new way. And so to get from grams of oxygen to moles of oxygen, we know 1 mole of oxygen is going to be 32 grams. So that's going to allow us to cancel out our grams of oxygen. And then we're going to convert from moles of oxygen, so moles of oxygen is going to go on the bottom, to moles of our water. And in this case, remember our mole ratio, so 2 moles of the water to the 1 mole of the oxygen. So that's going to help us cancel out moles of oxygen. And then at the end here, we're going to convert back to grams of water. So our 1 mole of water we know is 18.02 grams. So that's going to allow us to cancel out our moles of water. And so then when we do that math, we end up with 112.6 grams of H2O. Okay, now we did this calculation thinking maybe hydrogen was the limiting reagent. How much water could we make if hydrogen was the limiting reagent? Then we did the same thing if it was oxygen. Now we want to make a decision. And the decision is whichever one makes less is the limiting reagent. So that means oxygen was our limiting reagent, which means we only made 112.6 grams of water, and hydrogen was our excess reagent. Okay, so we would have had leftover hydrogen once we had used up all of the oxygen. Okay, and so that's how we do those limiting reagent questions. We're just using stoichiometry, same stoichiometry calculations that we learned in the stoichiometry video, okay? Only now we're doing it for both reactants to see which one is going to make the least amount of product. So oxygen is the limiting reagent because it made the least amount of product. Okay, so it made the least amount of product, which means it's the one that's going to run out first. And so that's going to be limiting to our reaction. Once we run out of that limiting reagent, we're no longer going to be able to make more product. We'll be finished making product. Okay, so then our other reactant, which in this case would have been the hydrogen, would be in excess. There would be leftover. Okay, so we're not actually going to make 400 grams of water. We're only going to be able to make that 112.6 grams of water. Now, how much product the limiting reagent makes actually has a special name. And it's called the theoretical yield. Okay? And so that theoretical yield is how much product can be made using up all of the limiting reagent. Okay, so if we use up all of the limiting reagent, how much product can we actually make? And so that is called our theoretical yield. Okay, now something else that we have in terms of a yield is called our actual yield. And our actual yield is the measured amount of product made in the lab. This is an actual amount. So when we actually do the experiment in the lab, this is from an experimental, like an actual experimental procedure. And actual yield is going to be what we put onto the balance to measure at the end of the reaction. Okay? And this is going to lead us to calculating percent yield. So our percent yield is actually our actual yield divided by our theoretical yield times by 100 to make it a percentage. Okay, oh, sorry, that shouldn't be a percent at the end there. Just times by 100 to make it a percentage. Now, again, this actual yield is measured in the experiment, okay? And the theoretical yield is using the limiting reagent, how much product can be made. Okay, so when we are calculating our percentage yield, we're going to take our actual yield, which is going to be measured experimentally. If you're doing a practice question, this number should be given to you, how much they actually measured on the balance. And then theoretical yield is using that limiting reagent to predict how much product could be made. Okay, and so our theoretical yield in our above example would have been that 112.6 grams for water. Okay, now let's pretend we did this actual experiment and we got 105 grams of water on the balance. So we measured it on the balance, that was 105 grams, and so that would be our actual yield. So then to calculate our percent yield, we take our actual yield of 105 grams and we divide it by our theoretical yield for that reaction, which was 112.6 grams. And then we times it by 100 to make it a percentage. So we get a percentage of 93.3%. Okay, that's a pretty good percentage yield. That means that we did the experiment pretty well. We got almost as much as we expected. Okay, now if you get a percent yield that's like 0% to say 50%, that generally means that there's a lot of experimental errors. Okay, so a lot of your product got lost somewhere, whether it got lost in transferring between beakers or it got lost because it got accidentally dropped or something like that. That's a pretty bad experimental error to get a percent yield that's less than 50%. Although sometimes it depends on the reaction. Some reactions don't work perfectly well, and so sometimes the reaction has a percent yield that's quite low. If you get a percent yield, 51% to that 100%, that means fewer experimental errors. Okay, and so you're doing a pretty good job with your experiment, and you're keeping the errors to a minimum. The closer up you get to 100%, the better your experiment went in terms of not having very many errors. Now, if you have a percent yield that is greater than 100%, that also means experimental errors. Because you can't actually make more than what is predicted. And so usually that means that your actual yield was incorrect. Okay, and some reasons for this. The most common reason is that you have a solid being produced, but you measured it when it was still wet. So you're trying to measure the solid being produced and you put it on the balance, but the solid hasn't fully dried. And so you're actually measuring two products. You're measuring the solid and the water that's surrounding it. And you don't want to measure both products at the same time because you only want to compare one in terms of amounts. And so that's the most common problem if we're getting percent yields that are greater than 100%, is that a solid that we're measuring at the end with our actual yield of the experiment was actually not dry. And so we are not able to actually measure the amount of the solid. We're measuring other things as well. So that tends to be the most common error in that greater than 100% yield. All right, so that's it for theoretical yield. Okay, again, the calculation is not new. It's stoichiometry calculations. And then that's also it for percent yield. Okay, so pretty straightforward formula there for percent yield. So now you want to make sure that you're doing a lot of practice. So doing practice with the limiting reagent questions as well as the percent yield questions. And so that's the end of this video lesson.